If you tried to land a spaceship on Jupiter, you would never hit the ground, but you wouldn't float harmlessly through a cloud either. For generations, we have been teaching the world a fundamental lie, that Jupiter is a gas giant. We imagine a harmless, balloon-like world where, if you could survive the crushing gravity, you could fly your ship right through the other side and emerge out the back. That idea is completely wrong. The reality of Jupiter is far more terrifying and strange than a simple ball of gas. It is a world where the physics we understand on Earth begin to break down entirely. It is a planet that shouldn't exist, holding an ocean so vast it defies human comprehension, and a core that has baffled the brightest minds at NASA for decades. The Jupiter you see in photos, the stripes, the swirls, the hypnotic beauty of the Great Red Spot is just a mask. It is a deception. To understand what this monster actually is, we have to strip away the clouds and dive into an abyss that transforms matter into metal and dissolves rock into rain. Before we dive into those clouds, look down. If that subscribe button is still red, click it right now. We explore the universe's darkest secrets every day, and you don't want the algorithm to hide the next discovery from you. Most people look at the night sky and see a bright star. Planetary scientists look at Jupiter and see a mystery that threatens our understanding of how solar systems are built. Today, we are going to look at what actually lies beneath those clouds. We are going to find out why Jupiter is not a gas planet at all, but something far more substantial and far more dangerous. To understand why we got it wrong for so long, you have to look at how we first saw the king of planets. In the classrooms of the 20th century, the model was simple. You had the rocky inner planets and you had the gas giants, big, fluffy, low-density worlds. In the 1970s, humanity extended its reach. We sent engineering miracles like Pioneer 11 and Voyager 1 to fly past the outer solar system. These missions were humanity's first real look at the neighborhood giants. They sent back those iconic, grainy images that defined a generation's view of the cosmos. We saw the violent storms. We saw bands of ammonia clouds whipping around at hundreds of miles per hour, creating turbulence that dwarfed entire continents. We saw the Great Red Spot, a hurricane twice the size of Earth that has been raging for centuries. But there was a severe limitation to these missions. Voyager was essentially taking a photo of a wrapped present. The cameras could analyze the light bouncing off the tops of the clouds, but they couldn't see a single inch below the surface. Because the planet was so massive and the average density so low compared to Earth, the assumption remained simple. It must be gas all the way down. A giant, swollen star that failed to ignite. We became comfortable with this theory. It was neat, it was tidy, but planetary science is rarely neat. While the Voyager images were beautiful, they were superficial. They hid a violent secret. We needed something to punch through that outer shell and show us the blood and guts of the planet. We didn't have a drill big enough to do that. But in the 1990s, the universe decided to do the drilling for us. The turning point for our understanding of Jupiter didn't come from a quiet calculation in a university lab. It came from a cosmic catastrophe. In July 1994, a comet named Shoemaker-Levy 9 ventured too close to the giant. Captured by Jupiter's immense gravity, the comet didn't just crash, it was torn apart. The tidal forces of the massive planet ripped the comet into 21 distinct fragments, creating a string of pearls roughly 1 million miles wide. The entire scientific world turned its telescopes toward Jupiter. They waited, and then they watched in horror and fascination as those fragments slammed into Jupiter's southern hemisphere. This wasn't just a meteor shower, this was an orbital bombardment. The fragments hit the atmosphere with the kinetic energy of millions of nuclear warheads detonating simultaneously. The explosions were so massive they created fireballs larger than the Earth itself, rising thousands of miles above the cloud tops. They were visible even through amateur backyard telescopes. But for scientists, this wasn't just a spectacle, it was a biopsy. The impacts punched deep holes in the cloud tops, dredging up dark, sooty material from the layers beneath that had never seen the light of the sun. For the first time, we weren't just looking at the skin of the planet, we were looking at an open wound. The scars left on Jupiter remained visible for months, dark black bruises against the pale clouds. This dark material gave us the chemical signature of the interior. It changed everything. It set the stage for the Galileo mission and later the Juno spacecraft to rewrite the textbooks. They realized that the gas was just a thin veneer. The real monster lay below. Let's simulate a descent into the planet based on the data we have now. If you were to drop a probe into Jupiter, here is what it would experience. As you drop through the outer atmosphere, you pass through the layers we know. white ammonia clouds, violent lightning storms 10 times more powerful than anything on Earth, and winds screaming at 400 miles per hour. It's a chaotic, freezing cold gas environment. But as you fall deeper, the concept of a surface becomes meaningless. On Earth, there is a clear, distinct line where the air ends and the ocean begins. If you jump in, you splash. On Jupiter, there is no splash. As you descend, the pressure mounts relentlessly. The hydrogen gas around you gets thicker. The view outside goes from clear to foggy to an impenetrable soup. The gas is being crushed so hard that it enters a state called a supercritical fluid. It ceases to be a gas, but it isn't quite a liquid yet. It is a thick, hot sludge. Eventually, the pressure becomes so crushing, millions of times the atmospheric pressure of Earth, that the hydrogen gas is forced to change state entirely. It becomes liquid hydrogen. This is the first great secret of Jupiter. It is not a gas giant, it is a liquid planet. Beneath the clouds lies an ocean of liquid hydrogen. This isn't a small underground lake. It is a global ocean thousands of miles deep. It is the largest ocean in the solar system, vast enough to swallow every other planet combined. It spins and sloshes, creating internal dynamics that drive the massive storms we see on the surface. But if you think a liquid ocean of hydrogen is strange, what happens next is almost impossible to visualize. We are now thousands of miles down. The sunlight is long gone. The temperature is hotter than the surface of the sun. The pressure is unrecognizable to human physics. We have left the realm of normal liquid, hydrogen. At these depths, the hydrogen atoms are squeezed so tightly together that the structural integrity of the atom fails. The electrons are stripped away from their protons. The hydrogen loses its identity as a gas or a normal fluid. It transforms into something that exists only in the most extreme environments in the universe. Liquid metallic hydrogen. This substance acts like a metal. It is fluid, but it conducts electricity. Imagine a sea of liquid copper or mercury, but made of the lightest element in the universe. This churning, spinning ocean of metal is the engine of the planet. Because it conducts electricity, its movement generates a magnetic field of terrifying power. This is why Jupiter's magnetic field is 20,000 times stronger than Earth's. It creates a magnetosphere so large that if you could see it with the naked eye from Earth, it would appear larger than the full moon. This metallic ocean is the true body of Jupiter, a swirling, conductive dynamo that acts more like a star than a planet. It is this layer that protects the planet, but also makes it incredibly radioactive and dangerous for any spacecraft to get close. Finally, we reach the center, the core. For decades, the prevailing theory was simple. We believed that inside all that gas and liquid metal, there was a solid rock seed, a heavy, rocky, metallic ball about 10 times the mass of Earth that acted as the gravity anchor for the planet. We assumed it was like a cherry pit inside a fruit, hard, distinct, and solid. But when the Juno spacecraft arrived and performed gravity mapping of the planet, it returned data that shocked the mission controllers. The core wasn't solid. It wasn't a hard ball of rock. The data suggests that Jupiter has what scientists now call a fuzzy core. Imagine dropping a sugar cube into a cup of extremely hot tea. If you look immediately, the cube is solid. But if you wait, the cube starts to dissolve, spreading out into the liquid. It becomes a dense, sugary region rather than a solid object. That is Jupiter's core. It is a diffuse, mixed region where rock, iron, and ice have dissolved and blended into the metallic hydrogen above. It has no sharp boundaries. It extends outward, mixing with the layers above it. Scientists are still arguing about how this happened. Did a massive collision with another protoplanet early in the solar system's history shatter the original solid core, spreading it out like paint in a bucket? Or did the planet form in a way we simply haven't modeled yet? Jupiter challenges everything. It forces us to rewrite the definition of a planet. It is not a cloud. It is a distinct, layered beast. A thin atmosphere, a deep liquid ocean, a metallic mantle, and a dissolved fuzzy heart. The more we look at it, from the scars left by Shoemaker Levy 9 to the gravity maps of Juno, the more we realize how little we actually know about planetary formation. We live in the suburbs of a solar system dominated by a liquid metal monster, and we are only just beginning to scratch the surface. The image of the peaceful, gassy balloon is dead. In its place is a dynamic, liquid world that bridges the gap between a planet and a star. If you want to keep exploring the deepest mysteries of our universe with us, make sure you hit that subscribe button and turn on notifications. You won't want to miss what we uncover next.